So here we're going to look at displacive phase transformations. And so this is a little bit different, actually quite a bit different than the reconstructive phase transformations that we discuss in another video. So displacive transformations, these involve a bending of bond angles. We're not going to rip apart the structure. Remember, in reconstructive, if you've already seen that video, we're going to take the bonds, break them, and then reform them into a new pattern. Here, we're going to get a new pattern by taking certain bond angles, and you can see we have some right angles here, and then bend them. So now things are not quite the way they're situated as they are in this upper figure over here. This is a diagram, figure 12.4, from the mineralogy textbook by Klein and Dutrow. So in this example here, we have some tetrahedra. They could be filled with aluminum or silicon. For our purposes, it doesn't really matter. It kind of more or less mimics the structure that you might see in a plagioclase feldspar, but it's not really meant to mimic any particular structure. So we have something here where we're not going to break any of the bonds. So this bond won't be broken. This shared oxygen over here won't be broken. None of these bonds are going to be broken here. We're just going to bend them. And so instead of these guys being horizontal, they're going to be tilted at this cockeyed angle over here. And you can see that that breaks the symmetry. So we have very nice symmetry here. We could put a mirror plane there and a mirror plane there. But if we start bending those angles, then some of those mirror planes disappear. For example, there's a mirror plane that's still vertical. This stuff over here is the mirror reflection of this over here. But we no longer have this horizontal mirror plane that we can draw. So we've broken up some of the symmetry, and we've changed the structure. We've changed the point group or the space group of the mineral. So if we're just bending the bond angles, we'll just put bond over here, so it's the bond angles that are being changed. What does that mean for the transformation? Well, the reconstructive transformation was slow, but these tend to be fast. It's much easier to bend the bonds rather than break them, and so it's much more easier to get the reaction to go. And then they are also much more easily reversed. If we bend them one direction, we can bend them the other. We don't have to put in energy to breaking all the bonds and then reforming them. So these are going to be much more easily reversed than they will be in the reconstructive case. Just to take one example, we looked at the SiO2 system in reconstructive. We can look at another pair of phases here. We can look at so-called high quartz, and it can transform to something called low quartz. And so we'll just abbreviate that as QTZ. I think we're getting off the edge here. So high quartz has a space group that is P and then 6 sub 2, 2, 2, whereas low quartz has a similar space group, but not exactly the same, P 3 sub 2, 2, 1. So these are different space groups, and it collapse to different point groups as well if you eliminate the translational symmetry. We get this change in symmetry by bending the bond angles, not by breaking them or rearranging them. So it's a little bit easier to go back and forth between low quartz and high quartz than it would be to go between, let's say, low quartz and cristobalite, where that would be a reconstructive or first order kind of transformation. By the way, when we referred to the breaking of bonds and reconstructive as first order, displacive would be an example of second order. So you might see a transformation being referred to as displacive or second order. Those are essentially the same.